Let's talk about the HVDC Classic. HVDC Classic is based on thyristor technology. AC transmission over long distances has a problem. The series line reactances block AC and the parallel line capacitance short circuit AC. The longer the line is, the stronger this effect will be. So you have to push a lot of power into the system in order to get a little bit something out at the end of the line. On top of it, AC produces reactive power. It produces losses due to reactive power. It produces additional losses due to the skin effect. A skin effect is an effect which reduces the cross-section of a conductor which is utilized at higher frequencies. AC has angular stability issues with long lines, and AC requires huge space for the corridors. Therefore, for long distance transmission, HVAC is not the solution of choice. It's more and more replaced by HVDC. HVDC is the best solution for very long transmission distances. I'm talking about normally above 1,000 kilometers. For cable, however, the distance where you can transmit something meaningfully is something between 30 and 50 kilometers. This is basically due to the dielectric constant of the cable insulation, which increases dramatically the capacitance between the inner conductor and the outer shield. And therefore, the stray capacitance is bigger, and therefore AC are short-circuited for longer distances. The usage of HVDC cable systems is increasing because of all the subsea connections, all these interconnections which are built today. This is a schematic of a HVDC transmission. On one end of the line you have AC, then you have a converter converting AC to DC, and at the end of the line you have a second converter converting back DC to AC. To the basic working principle of a converter, this is a normal AC circuit without converters, so you have the source, AC source, and you have the AC load. This is now the simplest form of a converter, or better rectifier. It's just a diode, which is passing the current only if it is positive, otherwise it's blocking. Here you have a full bridge rectifier, which is passing both half cycles. So it is flipping both half cycles from negative to positive. Now you can see how it works. Depending on the polarity of the cycle, one or the other diode pair is acting. You note that the DC here with this simple rectifier is quite bumpy. So in reality that would create a lot of noise. So you can connect a parallel capacitor to the load so you can smoothen the DC current or voltage. That will reduce the noise. So far we have been looking at diodes only, but I would like to be able to control the amplitude of my DC voltage, and therefore instead of diodes we have now thyristors. And here you can see in this small movie how the thyristors can control the amplitude of the DC voltage. This is the same circuit as before, but here I have now a smoothing parallel capacitor, and you can see how the effect works. In order to further smoothen my DC, instead of going with one phase only, I go with 3 phases, and then I move to a 6-pulse full bridge rectifier. And if I want, I can also introduce a smoothing capacitor, and then you have already a pretty smooth DC. Here I have now replaced the diodes by the thyristors, so I can control the DC part, as you can see now. And on top of it, I insert, if I want to smoothen the DC, I insert a reactor. So instead of a capacitor, we have here a reactor. Beautiful, huh? And now, ladies and gentlemen, the final move. I move from a 6-pulse full bridge rectifier to the HVDC rectifier, which is a 12-pulse. And in order to get the 12-pulse rectifier, I have to add a transformer, and one of the transformers is star-star, the other one is star-delta, and therefore I have a phase shift between the two 50 Hertz components. I put them in series, and then I have a 12 pulse, and this is exactly what we normally have with a conventional HVDC. Here, look at how it works. You can see how I can control now my HVDC. And if I insert the reactor, the DC is now pretty smooth. The way the curves jump a little bit because of the automatic adaptation of the resolution. So this is now really the converter we will utilize for an HVDC system. What you can see now is the same converter as shown before, but at both line ends. So we have converter 1, converter 2. The line is represented by a series reactance and a series resistance. This series resistance is extremely important because you will control the power flow by controlling the current. And how do you control the current over a resistance? You have a voltage across the resistance, and this voltage across the resistance is the difference between the sending end voltage and the receiving end voltage. So you control the current by adjusting the difference between the sending and receiving end, and this is how you control the power in HVDC.
By the way, the resistance is of course the line resistance. It's not a lump resistance.
You also see is that the polarity of the thyristor is different from the sending converter to the receiving converter, and this also means that the current can flow only in one direction. So the current is always flowing according to the polarity of the thyristor. That means if you want to revert the power flow, you cannot revert the current, but you have to inverse the voltage. So power flow from left to right is achieved by a positive voltage. Power flow from left to right is achieved by changing the polarity between the sending and the receiving end. So both are either positive or both are negative. And this is how you can change the power flow in HVDC. So you control the difference in voltage at the sending end and at the receiving end. So the circuit I show here is a strong simplification. In reality, of course, you would have a series reactances at the source. You would have reactances within the transformers. You would have reactances and filters and whatsoever on the sending and on the receiving end, and in series to each of these thyristors. So the real circuit would be much more complex, of course, but just for simplification and for also speed of calculation, I simplified the circuit as you can see it here. But the disadvantage is, of course, that it does not work that well.
I will now build a case on my simulator. Let's see how such a circuit is built up.
So this is now my HVDC system. I can control the power flow. Power basically is the red one. You can see here the AC power of the AC source, and on the right side I just have the DC power, and I can now control the amplitude of the power by controlling the trigger point of my thyristors on the valves on both sides. And if I increase the voltage delta between both line ends, I will increase also the current, meaning I increase the power flow. As you can see here, the power goes up now. Anyway, you can go to the simulator. The circuit is already there. You can just switch it on, and then you can play around with it in order to learn how this works to get a feeling.